This is Q-PAC's new airflow tunnel. Finally done, starting to get operational. We're really building up the capabilities and capacity with this thing. And so we're gonna do a quick rundown and overview of it. You're gonna see all the parts and pieces, what's running, how it's running, why we built it the way that we built it, and some of the tests that we're excited for in the future, and what we're looking to do in the very short term. So we're gonna meet with Brian and Ken, the research and development guys that are really making the future possible. And man, it's gonna be pretty cool. So let's go check it out. So we're standing in front of Q-PAC's airflow tunnel?
We are standing in front of Q-PAC's airflow tunnel.
All right, let's just start with the basic. What do we got?
What do you have? We have a 12 by 12 foot wide by 12 foot high airflow tunnel. On our right side, we have our test fans. On our other side, we have some supply fans to push air through there. We can get 70,000 CFM through this tunnel, all the way down to 2,000 CFM we can measure. Why do we need an airflow tunnel? We need an airflow tunnel to make sure, first of all, that what we're putting out there works to our specification. But secondly, and more importantly for me as a research and development engineer, so we can find new ways to make better fans.
Cool, I dig that. So there's a huge amount of capacity and capability in this thing, right? So
huge.
How about you start us from one end and walk us
Sure.
through what each part does and kind of
Yep.
what we're looking at and why.
What we're looking at and why, absolutely. So I think maybe we'll start at the business end of the thing that's being tested. So we're going to walk through the safety cage here. We have actually a couple of apparatuses, a couple of tests going on through here, some other fan research going on here, and that's what most of this equipment is. But what we're looking at here is a set of 4 test fans that is similar to what you'd find in a multi-motor plenum fan. We have the Q-PAC fan controller here. So this is the test fan. This is the equipment under test. This is what we'll be measuring the performance of, what we'll be doing experimentation on. We have it instrumented several different ways. We have laser tachometers here to give us an independent measurement of the speed of the fans. We have Modbus hooked up to give us instrumentation and insight into what the motor is doing. And all the way to the right, we have a giant piece of copper windings inside that shell, which lets us vary the voltage from 200 volts all the way up to 600 volts so that we can see and measure the impact of voltage on the performance of the fans.
What are you expecting to be the impacts of that voltage on the fans?
Well, of course we know that as we lower the voltage, in order to maintain the same amount of power, we have to raise the current. The more current you have, the more heat loss you have through the wiring. So we know that's an important factor. But there are other things we can do besides just varying the voltage straight up. We can vary voltage in different phases. Most of our motors are 3-phase motors. So we can see the impact of losing an entire phase and maybe make some mitigation strategies. We can look at the effects of injecting harmonics, removing harmonics. And all those things are things we can characterize and measure with the equipment we have here.
Cool, and just a general kind of stupid question, why is it important to measure so many things when it comes to airflow in a commercial setting?
The fan manufacturers have characterized their individual fans and motors combinations really well. We know the performance of a single fan. The industry really doesn't know what happens when you put 4 fans together in a spacing of what we have there is a fraction of a diameter versus when they're spaced out a full diameter away from each other. So we use fudge factors in a manner of speaking. The industry accepts that because that's about the best data we have. We know we can do a lot better than fudge factors. It's just a matter of measuring it, characterizing it, and then modeling it so that what we measure in a few different test setups can be applied across an infinite range of an infinite range of installation setups. So that's why we want to measure it. That's why we want to characterize it. We'll model it, and then we'll be able to tell you when you're speccing your equipment exactly what it's going to do, and you'll be able to trust that.
Cool, I dig it. Trust is important in this industry, that's for sure. So how about you keep walking us down the line? What do we got next?
Right, so we'll be able to see what's in that section from the other side really. It's important, it's imperative really, when we're testing the fan that we know what the airflow is going into the fan. If the air is turbulent, if it's flowing around backwards and forwards, your results are not repeatable. You can't really trust the results. So in this section behind this beam here, we have a series of flow straighteners. And so you'll be able to see some of that coming through here. Looking to the right here, you'll see an aluminum grid there. Behind that, there's a finer grid. And behind that, there's yet a third grid. And all that's doing is dispersing the air so that it hits the fan, passes through to that 12 by 12 foot section. On the other side, it's coming out even. So that every fan that we have in the array is seeing the same airflow. On the left, it gets a little more interesting. What we have here is one of the most unique features of this airflow tunnel, of any airflow tunnel, in fact. Because we need to collect so much data, and because we're going to go over such a wide regime of airflows, 2,000 to 70,000 CFM, we're going to be changing the amount of airflow a lot, which means to measure that airflow correctly, we need to change the nozzle configuration a lot. And so what we're seeing here is the backside of the nozzles and the actuators that will let us automatically change the number of nozzles we have open or closed as we're progressing through the test. For testing a particular fan array, we're looking at somewhere in the neighborhood of 100 test points. And to go in here and change nozzles one at a time manually means shutting down the tunnel, cutting power to safely walk in here, reconfiguring it, coming back out, and restarting the test. In order to collect the data quickly, efficiently, we have designed this tunnel to be fully automated.
So I'm going to ask you a couple questions really quick while we've got
Sure.
this open. So we were talking yesterday, and you were saying that they only fully open or fully close, and that you can only do it in sections. Why is that?
Right. So each of the 16 nozzles is either fully open or fully closed. The nozzle profile, we'll see it a little better from the other side, has a specific geometry, and we know through actual physics that the pressure difference from one side of that nozzle to the other, combined with the geometry, tells you exactly how much air is flowing through that nozzle. If we partially closed it, all those assumptions go out the window, and we really don't know what we're measuring anymore. So we either open it or we close it. And you can see one there about to pan across has that open. You can see the white inside of that nozzle. So that one is fully open, and all the rest of them are fully closed at the current time.
Cool.
Let's check out the other side of those nozzles. We can look at that geometry. So you have to come around this way. Very good. So what we have there are fiberglass nozzles that have been built to a very specific dimension. That dimension is built to an AMCA standard, so that we can use the AMCA standard to tell us the airflow.
Why is that important?
That's important. It's very important. It's something I neglected to mention earlier. Is this tunnel was built, purpose-built to meet the AMCA 270 standard. AMCA 270 is a fan array standard for building a instrument to get reliable data for fan arrays. But that profile has to be exactly to the thousandths of an inch correct, so that when we're measuring pressure difference across that wall, we know that we're measuring against a specified geometry. So we don't actually measure air directly, we measure pressure between this wall and the wall we just looked at, or the room we just looked at. That pressure difference times the number of nozzles open, times the formula for that particular nozzle, tells us the airflow we have flowing through there.
That's pretty cool.
And so that's one of the three most important measurements we're doing is the amount of airflow. The second one I didn't mention when we were over there in that first section is the pressure, right? So we can measure the static pressure across the fan wall. So we have airflow and we have pressure. Those two numbers will let us build the fan curve. So tell us the performance of that fan. The third thing we measure, which I did mention, is the power. By measuring the power, the airflow, and the static pressure, then we can generate the power curve and calculate the efficiencies. So all of this tunnel was built for to calculate those three things accurately. A common question I get about the airflow tunnel when you really get into it is if the system is specified for, say, 3 inches of static pressure, But your fan is over here exhausting into the air. Isn't it exhausting into zero static pressure? And how can you measure that if you're just blowing it out into the open air? And the answer is, we don't actually care about the absolute pressure. We care about the pressure difference from the intake side to the exhaust side. So if we're blowing at atmospheric pressure here, we actually have to have negative pressure on the inside of the fan. So most of the time, for most of the testing, we will actually have negative pressure in the airflow tunnel. Because again, we only want that pressure difference. Lower on the intake, higher on the exhaust side. And higher, because we're blowing into the air, is always going to be basically zero pressure.
And with negative pressure being in the airflow tunnel, we wouldn't expect to see any difference between that and a real life application.
From a physics point of view, it is absolutely the same thing. It is only in your air handler here in the tunnel, you're always worried about pressure difference. You're not ever worried about absolute pressure.
Cool, that's awesome. All right, why don't you take us through, I think, the last section, right? The fourth section?
Yeah, and since we're going to pass by it, we might stop here at the brains of what operates the tunnel. Of course, we have a lot of electronics. There's a control box there that operates most of the sensor equipment. We have a control box here, which is operating the supply fan, and we have an interface to all that stuff. The fancy one over here is actually our controller for the supply fan, which we'll get to next. And we have 14 fans for that, and a way to control those. We were just talking a little bit about pressure and airflow and the duty point. So we have some software here that lets us model that, predict that. For different fan models, we can put in whatever size fan array MPF we want to test. And then this is the actual software in its current state for running the test. We can control how many nozzles are open and closed. We can set our set point for CFM, and we can monitor the pressure. And then from those things, we can walk across the curve and generate our points to calculate our fan curves and collect whatever other data we want. Of course, data logs does all that stuff. From that data, we can generate the data we need to create an AMCA 270 test report, and from there you can certify a particular fan.
Cool. All right, take me through.
All right, we are into the last section. We talked about some flow straighteners going into the test fan. Also on the right here, we have flow straighteners going into the nozzle section. That's because we need to make sure every nozzle sees the same airflow. Because we measure pressure difference across the whole section. If the different nozzles are seeing different pressures, then that's going to throw our number off. So we need to get clean airflow into each of those nozzles.
Do you have the same amount of layers on that side as you did on the other?
We actually we spec'd 3 layers on this originally. It turned out that we got better airflow with just 2 layers of diffusers here. So we just have 2 here. We have the capability to add that if we ever change something in our flow regime. For instance, if maybe we changed out our supply fan for some customer's air handler, and that changed the flow coming into the screens, maybe we'd change out the screens for that. It is an interesting feature, a very unique feature of this airflow tunnel, is that this fan unit is modular. It can be pulled away, and we can substitute any other equipment in here. One question you might ask is, why do we have fans here at all? Weren't the test fans over on the other end of the tunnel? Well, the answer is, if we didn't have any fans here, if we just had an opening, and we were operating our test fans at a certain speed, that resistance to flow through the tunnel is going to give us a certain pressure. But we need to be able to test the different pressures for the same speed. Because when you walk across the fan curve, you're going, if you go from bottom to top, you're going from higher flow and lower pressure to lower pressure, and to lower flow and higher pressure. And if the only control we have on that end is speed, then we have to be able to control either the airflow or the pressure some other way. And what we do is control the airflow by adding or reducing fans on this side. So that's why you have these fans. So basically, supply makeup air and overcome the resistance of the tunnel to get to the pressure and airflow speed we need for the duty point we're trying to test out.
Cool. That's going to bring some exciting tests down the line where we can swap a bunch of things out and kind of try everything, and this guy over here is going to talk to us about
He's
that
going
in
to
a
talk to us about
second.
that. He is going to talk to us about that. Yeah. And not only can we swap different supply fans here, if we need to, we can actually swap ends of the tunnel and move this fan to the front side, the exhaust side, and the test item to this side. So if there are reasons, for instance, if we're bringing in someone else's air handler that we want to test in a different configuration, we have that ability. I mentioned switching out, turning on and off different fans. We also have dampers in front of those that are automatically actuated so that we can also restrict the airflow along with the supply fan.
Nice.
And I think we've covered most of the features of this tunnel.
Yeah. No, this has been great. This is an awesome walkthrough, and just the capacity and the capability is we're just scratching the surface,
Just
right?
scratching the surface. Yeah.
Cool.
Cool.
Well, thank you so much for your time. That was an awesome
Thanks,
tour.
Eddie.
All right, Ken, so what are you going to walk us through over here?
All right. My name is Ken Nguyen. I'm part of R&D department here. I get a lot of questions about on the customer or the people visits and say that why we build it airflow tunnel the way we build it and what we use it for. So in a nutshell, we want to come in with the attitude, right? We want to solve the biggest problem of the fan industry. And with that, we have our mindset about our future product. And our future product requires something that never been done before, include the airflow tunnel, the process of testing that never been done before, right? So AMCA 270 is the newest accreditation type of airflow tunnel that allow us to test with multiple fan, which is air source, that with the dynamic effect. And this new accreditation process require a new type of airflow tunnel, new type of accreditation, and that's why we build this. So to answer or to solve this problem of the airflow with the attitude, we have a mindset for a product. And from that, we combine with physics and engineer to solve the problem. That's in a nutshell why we build this. Okay. Again, this airflow tunnel is AMCA 270 airflow tunnel. The capacity of this airflow tunnel, they can run from 2,000 CFM up until 70,000 CFM. So it's a wide range of operation according to because we have a wide range of operation on our product. So this is we want to make sure that we can cover and test out all the range that we apply to.
Why did we stop at 70,000?
Actually, good question. 70,000 CFM is not the biggest airflow that we produce on our product, but that's enough for us to test all the dynamic effect if we lay it out certain way. And I will explain a little bit deeper as we go into this presentation. Again, we also want to push it all the way to the highest static pressure that the industry will require, which is 12 inches of static pressure this airflow tunnel can handle. And it's not just positive or negative pressure, it's negative and positive pressure at 12 inches. So the difference is 24 inches of static pressure if you add them together. Okay, so negative 12 and positive 12. Why we doing this? Because we can test the air handling unit to push the air through this airflow tunnel. While we can test the fan working along as a fan itself. So that's why we design that way. Voltage range, we can test up to 2,000. We can test up to 600 volt AC and at 200 amp power. So this is a really large power can be in here. So power measurement, we also use individual and as well as like multiple like individual fan power, and as well we can use system fan power measurement. So for the research purpose, we have the own weather station to convert the actual pressure and temperatures and humidity into basically a standard, so we can calibrate all the difference in the density of air. Flow measurement, we also we make custom made 16 cones, which you probably gonna already see in the walkthrough of the airflow tunnel. That combined with that 16 fan allow us to test a wide range of testing capability. Again, system control. This system control is not just to control the airflow tunnel, how it works, but it also built in something very unique, which is machine learning capability to feed the data. Technically, if you build an AI system, this is how you generate data for the future of the extrapolation of the fan performance, right? So, for example, the system gonna predict the performance of the testing fan, but every time we testing it, the system will automatically correct in it because of the real data might be deviate from the estimation. It will create its own correction equation and to correct in it for better accuracy the next time that you use the airflow tunnel for predicting data. Because the amount of testing that required for multiple fan work together and the product permutation of the fan, how they produce, it's so many factors that affected the dynamic effect and the performance of the fan. We use the testing combined with software and data in order to extrapolate all the data for, to reduce the amount of tests that we have to do in order to cover our whole profile of products. So that is a nutshell of the airflow tunnel, how it's designed. In here that we want to show a diagram of how the airflow tunnel, again, the airflow tunnel is designed from AMCA 12 and AMCA 15. What is the difference? That means our test fan is exhaust, or our test fan could be provide the air into the airflow tunnel. And if you looking at this configuration, if this is the air handling unit provide the air into the airflow tunnel, we can use the tunnel to simulate every single, like the ductwork, the effect of the coil, how the fan would behave to it. So this is how we test at the system level. And this is how we test at the fan level, which is the configuration of the airflow tunnel right now. It's testing the fan. That means the supply fan providing the airflow into the airflow tunnel, and that control the static pressure and the air volume of the testing. The other unique feature that we build in this system or this airflow tunnel is it can able to identify how many point of testing in order to fall within certain range of percent of error. For example, if you want 2% of error, within 2% of error, how many points that you have to test, and all this is automated, fully automated by the airflow tunnel. So we don't have to do it. Most of the airflow tunnel today is actually manually, you have to pick the point and test it. This airflow tunnel pick its own point.
So why is this important for the people at the end who are looking to buy this kind of stuff or bring this into the building? What kind of knowledge is this going to unleash for them?
So in terms of like making air handling unit or making the airflow tunnel?
Either. Like what do you see as the biggest value in being able to have this capability that's not been seen in testing air handlers and fans before?
Okay, yeah. So for us, because like I said, because we want to see the dynamic effect of multiple fans that working together. So, and because of the testing, the capability of this airflow tunnel, it can answer you a multiple things. It can see how the fan work dynamically together at the fan level, or a single fan level, at multiple fan level, or at the air handling unit level. So that's why this design is important. At the development level, by precisely can control and automate this whole system, we can have ability to build in the automatic test process that allow us to cut like almost 80 to 90, like 80% of the amount of testing that we require to hit the certain point, because we're using software and data to extrapolate the data, and then we need to test for only a few verification points in order to make sure that the system it predict and also extrapolate accurate enough for the AMCA to meet AMCA accreditation or certification.
But our biggest priority is testing to be AMCA certified. Ken, why is that important?
Okay, so yeah, it's very important in terms of the accuracy because technically, if you looking at any equipment manufactured today or in the past, when you have a single fan, when air moving device that AMCA certified, that means they guarantee and almost meet the requirement of the performance, right? The public data is made by testing. Without the AMCA 270, if you put multiple fans together today, most of the data today that you can see from any fan design or multiple fan array design is an estimation, because they don't have any capability to test multiple fans together with a dynamic effect or at the system effect. So that required to put the AMCA 270 stamp onto the product, that also show our customer that the design of our product is actually accurate, not just by extrapolation, not just by expected data, but it's a real data. It's a real performance. That is why the AMCA 270 is so important, because that's required by the industry. But if you don't have a capability to test it, right now everybody basically just rely on the single fan performance, and then they basically kind of estimate the overall performance of the fan array or an MPF.
Right, so now you're saying we're certifying total systems, and not only that, it will have a stamp on it that says like this is legitimate data, it's not us blowing smoke or guessing.
Absolutely, yes.
That's awesome.
So that is the basic certification and accreditation of the airflow tunnel. But the real thing is we building this to build our better product into the future. And how we doing it? So like I mentioned before, this airflow tunnel built with ability to precision hit any set point and simulate at a system level. And because we can monitor the power, and since we can hit the precision in the application and in the set point, basically we can learn about if we can hit certain set point, what is the least amount of energy input into the fan system to hit that set point. This gives us a learning or machine learning integration into this airflow tunnel capability that allow us to learn and to using that logic that the airflow tunnel to run with the least amount of energy to better improve our product performance. So the testing is literally can be a learning at the same time. So this is on the overall, yes, it looks like airflow tunnel, but this is almost completely, if you add everything up together, it's a learning machine with data.
That's really cool. So Ken, talk to me. Are there any tests that you were excited to run personally, or anything you absolutely think we're going to find? Like you have a hypothesis that you're like, this is where I think we're headed.
Yep. So there is certain application that we see in the major industry today, including data center and in our air handling unit application that a lot of customer is really asking for. Is like, how do you know that the fan working at its best duty, or it can work in at best environment and maximize the energy efficient? Everybody talk about efficient. So the thing excited is, by using this automated system, you can actually allow the airflow tunnel to automatically find the sweet point of the fan system where it's got the most energy efficient. For example, sometimes that you have the air handling unit that you design or the fan system designed at 70,000 CFM. But certain time in the day, the fan system don't work at 70,000 CFM. It only work like halfway or even less than that. What is the best way to run this fan system? Deviate from the original design for, right? The seasonal chain, the airflow, the airflow through the building chain and this and that, right? Today we lock in to the way all the fans have to operate at the same thing. But in the future, you don't have to, right? Certain fans can be run idle or to lower operation point to save energy and to extend their lifetime. While the other fan, can switch their spot to get the least amount of energy and the most sufficient to run the system, the fan system, according to the environment it's provided. So this is a very new way to enhance fan efficiency at the system level. And the way we build it, airflow tunnel, is fully capable to automate that task, and that much shorter the testing time to require for that research and development. That's one of the things that I'm excited that we got to do first.
That's pretty cool, Ken. Man, thank you so much for your time. All right, so Brian, I got you back on screen. Ken just broke down the test that he's excited for. What about you? What's the test that you are excited for?
Well, first I want to say Ken was conservative in what he's excited for, because there's a lot that we want to test that we probably can't talk about. And so I think he was conservative. So what I'm going to do is tell you what I'm excited about, and then you're going to edit out the things that I can't talk about.
Oh, I don't even know what we can and can't talk about. So I'm glad my job is on the line too. But
That's right.
Hey,
That's
man,
right.
let's make some bosses upset. What are we excited about?
All right. So for me, I mean, I've got a pretty wide background. I've got a background in software, mechanical engineering, electrical engineering, test engineering, systems engineering. I have tests in all those domains that I'm interested in. Ken's very excited for the software stuff that he says I'm going to write. The self-learning stuff, that's really exciting. The tools we have today for making machine learning are just incredibly easy and exciting. So we're going to have a tunnel that's probably more intelligent than I am when we're done. I'm excited to build that, build it out completely. On the mechanical side, there's some fan stuff that I'm interested in.
I like that you called it fan stuff.
Fan
Stuff.
So there's my phone going off. One thing I want to talk about, which hasn't been talked about much lately. Well, let me back up a little bit. We talk about like designing for eco mode and finding the most efficient operating point for different duty points with a particular set of plug fans. What happens if you size some of the fans for your typical point and use a different size fan for your eco mode? Can you buy savings there? I'm curious to find that out. We've got some good theory, we've got some good math. We don't have data. I'm excited to get that data. We haven't really talked much about control algorithms, but behind some of the things Ken said are different ways to steer your system to the optimal point. We need to figure out what those algorithms are, design them, write them into hardware, and then test them with real data and see, does this method of control drive us to an optimal point? Does it drive us to an optimal point, but not the most optimal point? And there are other compromises we can make. We maybe can optimize performance by driving the fan a little above spec, or we can optimize for reliability by driving that fan well below spec. These are trade-offs we can make, and with gathering data, we can figure out what the cost of those trades are, so that we can build them into the customer's values and drive the fan not necessarily to maximize efficiency, but to maximize value coming out of the fan.
Yeah, that's a big question, is the value for people, right? Because efficiency, you're always going to be hamstrung some by the component, what's coming out in the hardware. Right. There's a huge amount of gain, I'm sure, with the software. Absolutely.
When you spec a fan, I mean, if you spec an efficiency, you can only really kind of pick an efficiency for one or maybe two operating points. And that locks you into being efficient at those operating points. Your system's going to evolve, your system may change, your overall system, not just your fan, your air handler. What you need for comfort cooling, your building space may change, the use of your building may change. Can we build that flexibility into our logic to adapt to what your need is on the day you need it, as opposed to you buy it once and you're locked in for 10 years?
Yeah, so these people are going to be able to buy an engine that's going to adapt to whatever this thing needs to drive versus locked in at that engine, operating at that speed.
Yeah, state-of-the-art flexibility today is, we can sell you a system and you can change its operating characteristics by flashing the firmware. That's state-of-the-art today. State-of-the-art for us for the future is you don't have to think about firmware. The system has already adjusted by the time you think you need something. That's where we're headed. That's what I want to design.
That's pretty cool. Man, thank you so much for your time.
You're welcome.